Hello everybody, my name is Søren Pike. I'm from the Microwave Lab Bremen. In today's lecture I would like to go over the maximum design of a small signal amplifier using a bipolar transistor. I would like to jump right into the maximum design of a bipolar transistor as we have done the basics in the last lectures before. Well, how to design an amplifier for maximum gain? Well, as you remember, in order to manipulate the gain of an amplifier, we have to select a certain gamma S on the input side and a certain gamma L on the output side. By choosing gamma S and gamma L, we can manipulate the total gain of the amplifier. As we know, the gain of the amplifier consists of three parts: the GS, which is the gain due to the input match; the G0, which is the internal gain, which is just S to 1 squared of the transistor S parameters; and GL, which is the gain due to the design of the load match. All three together give you the total transducer gain. Now, how to design for maximum gain? Well, we have to select our gamma S and our gamma L to be the conjugate complex of gamma in and gamma out. Let's go back to our little picture here. Well, when gamma S is a conjugate of gamma in and gamma L is a conjugate of gamma out, then we get maximum gain. This is due to the fact that a conjugate matching gives you the maximum power transfer from here to here over this orange line and from here to here over this orange line, and you automatically end up with a maximum gain. When you choose gamma S to be conjugate of gamma in, gamma L to be conjugate of gamma out, you get automatically the formula for the maximum transducer gain by just plugging it into the general formula. Well, we have done the unilateral case in the lectures. That's why I just switched to the bilateral case now. How to design an amplifier for a transistor which is bilateral? That's our question now. Well, in the bilateral case, our gamma S is equal to this value, and my gamma L is equal to that value here. Since gamma S and gamma L must be the conjugate to gamma in and gamma out, we have to set gamma S to be the conjugate of this and gamma L to be the conjugate of that. You see here already that you have to know, in order to pick gamma S, you have to know the S parameters of your transistor, and you have to know gamma L. In order to pick the gamma L, you have to know the S parameters and you have to know gamma S. And now you are in a kind of a catch-22 because you cannot pick gamma S because you have to know gamma L, and you cannot pick gamma L because you have to know gamma S. Well, however, there's a solution to that. These are basically two equations with two unknowns, and some smart people have figured out formulas for solving this equation system. This is a solution for this equation system where you want to maximize gain with a specific gamma S and gamma L. We can calculate gamma S and gamma L by this formula, and you need four intermediate parameters: B1, B2, C1, and C2. B1, B2, C1, C2 can be calculated by the S parameters only and by the parameter delta. Delta is nothing else but the determinant of my S parameter matrix, which is S11 times S22 minus S12 times S21. Now, once we have found B1, B2, C1, C2, we can plug in these values into this equations, and we get the gamma S and the gamma L. This is how you can find the required gamma S and gamma L for my bilateral design. Once you have done that, you can plug in the values into your GS, G0, GL formulas, and you can find out that GS is equal to 1 over 1 minus gamma S absolute value squared. G0 remains S to 1 squared, and GL is 1 minus gamma L squared over 1 minus S to 2 gamma L, everything squared. Now, after these steps, you have determined gamma S and gamma L, and you have determined the transducer gain in absolute value, and you can also convert it to dBs. Let's do an example. We can we can find a maximum gain amplifier for the BFP 540 transistor. The BFP 540 transistor is a typical small signal bipolar transistor which operates up to like 6-7 gigahertz, has a low noise figure, and so on. Now let's find a maximum gain amplifier for that transistor. In my example, I use specifications which are as following. I select an operating frequency of 5 gigahertz. I want maximum gain, and I choose a biasing point of my transistor to be VCE 2 volts and IC 3 milliamps. With the knowledge of the frequency and the biasing point, we can find the S parameters at this specific operational point for the BFP 540 transistor. How do we do that? We have to find the S parameters from a big list of S parameters which are provided by the manufacturer. These lists are so-called Touchstone files. You can download them from the manufacturer site, but you can also find the S parameter values directly in Microwave Office. And how to do that, that is what I'm going to show you in the next step now. Okay, we are now into Microwave Office. I started Microwave Office already with an empty screen. Now let's find the S parameters of my transistor BFP 540. We need to open a schematic, which is here, this part here, with a new name. I give it a name called Amplifier, and I create it. Now I have an open a new schematic sheet. I can place all my components on that sheet for the design of the amplifier. The first step is to import the transistor with the transistor data. We can find the transistor in the Elements tab here, and we use the manufacturer data, and the manufacturer data can be found in the so-called X libraries from Microwave Office AWR. We have to open up the library. We have to connect to the AWR website here. Takes a little while, and now we can download models from different manufacturers. We are looking for the BFP 540 transistor, which can be found under Parts by Vendor. And in Parts by Vendor, we know it's from INFINEON. So we go to INFINEON here. We use the linear model, which is under Data. And once we are under Data, we use RF bipolar transistor, because we know it's a bipolar transistor. And the BFP 540 transistor is a bipolar transistor up to 5 gigahertz. So we pick this list here, and now we see a list of various transistors for 20, 540, and so on and so on. We use the BFP 540 transistor. That's why we pick this model here down here, which is just called BFP 540. Don't use the other models. They are models for special housing types. Take the transistor and pull it over onto your sheet. Now you can see the transistor as a little schematic symbol, and also you can pick here your biasing point. In my case, I use a biasing point of 2 volts and 3 milliamps. Now we have set up our transistor already for the simulation. Well, we want to know the S parameters at this biasing point at 5 gigahertz. That's why we need to go through the list of S parameters and find the specific point and the specific set of S parameters. Once you have inserted this transistor into your schematic, you can go back to the projects page here. And then you will find under data files up here, you will find a data file called SFP540 S parameter. Click on that and you see that big list of S parameters for various biasing points and various frequencies. So you see here, for example, for the biasing point 4.5 volts and 6 milliamps, you have a list of S parameters for various frequencies. Since my biasing point is 2 volts and 3 milliamps, I go to find and say 2.0 volts, and then I'm already there. I have the biasing point 2 volts and 3 milliamps, and from that biasing point I have a list of S parameters. I want to use a design frequency of 5 GHz, and that's why I use this line here. This line contains the S parameters for my transistor at 5 GHz and the biasing point of 3 volts and 2 milliamps. The S parameters are given in the following format. You have to go back and take a look here. Frequency is given in gigahertz. S parameters are given in real and imaginary part. And the order is 1 1, 2 1, 1 2, 2 2. That means the following. Let's go back to our 5 gigahertz. The first two numbers here are S11, real part, imaginary part. This is S21, real part, imaginary part. This is S12, real part, imaginary part. This is S22, real part, imaginary part. So please write down these numbers as we use them in our design that's coming up. Okay, now we have found the S parameters of my transistor for the specific design, and we can go back to our theoretical design. Well, let's write down our S parameters for the frequency so we can use them for the further steps. I converted them to magnitude angle format. You don't have to do that, but it's more obvious to see what's going on. Here we are, my 4 S parameters from the Touchstone file I just analyzed. Now, next step is to plug in these S parameters into your formulas for B1, B2, C1, C2, and then you plug in these values into the formula for finding gamma S and gamma L. In doing so, we will figure out that my gamma S is 0.793 with an angle of minus 129 degrees, and my gamma L is 0.553 with an angle of 114 degrees. Write down these gamma values. You're going to need them for the design. Okay. Once we found gamma S and gamma L, we can calculate our overall transducer gain. In my case, my gamma S, which is this formula, becomes 2.694, or in dB 4.3 dB. Gamma naught is 404 or 6.07 dB, and gamma L is 0.856 or minus 1.67 dB. Adding them all together gives me an overall gain of 9.7 dB. That's the maximum gain you can achieve with this transistor at 5 GHz. There's no way to get more gain out of that, since we use the maximum gain design. Now, how to realize this maximum gain design? Well, we know our gamma S and gamma L having these values, and now we have to realize matching networks which give me this gamma S and this gamma L at these points. Let's start at the gamma L side. So when looking from the left into my output matching network, I should see a value of 0.553 and 114 degrees. That means I have to design an output matching network here that converts my ZL, which I assume to be 50 ohm, to my value gamma L, which is 0.55 114 degrees. This can be done using our Smith chart. We want to use transmission lines as matching networks. That means we are not going to use lumped elements. In order to do so, I like to use, as you remember, an intermediate step. I calculate matching network consisting of a transmission line and a capacitor in shunt. In the second step we can replace the capacitor in shunt here by an open-ended stub line. Okay, how do we get the gamma L which I need? Well, let's first mark down the gamma L in the Smith chart. Remember, it was 0.553 and 114 degrees. Well, the length of the gamma must be 0.55, which is this length here, and the angle is, from my real axis, 114 degrees. You can find these values in your official Smith chart here by this ring which is labeled angle of reflection coefficient. The length of this line you can find at the ruler where it says EOI of reflection coefficient. Okay, once we have marked that point, you know where we should end up with our matching network. On the other side, we start our matching network at 50 ohms. 50 ohms is in the center of the Smith chart. Now, how do we get the point here, center of Smith chart, to this point here, gamma L? Well, we need these two elements. First, capacitor in shunt, which is this yellow line. Putting the capacitor in shunt follows this yellow line. We end up at this intermediate step here, and then inserting a line moves around the center and brings us to this point. So first step is to find this intermediate point. This intermediate point is the intersection of this circle here around the center and of my blue admittance line shown here. Okay, step one, once again, moving to this intermediate point with the capacitor and shunt. Step two, moving to my gamma L using inserting a line. Now, let's write down the number of the intermediate point, which is 0.36 minus 0.48J impedance, or 1 plus 1.34J admittance. Now, next step is to find the values of my inserted line and of my capacitance here. The capacitance value is, well, just in terms of admittance, we have to change our y value from 1 to a y value of 1 plus 1.34J. So let's write down that. My y value of my capacitor needs to be 1.34J, because 1.34J brings me from this point to this point in terms of y's. So, second step is to determine the length of that line. Let's do this in the next slide. We start here at this intermediate point. We end up at my gamma L point. Well, this is now very easy. We just have to look up our starting point of in terms of lambda, which is 0.422 lambda on that outer ring, and we have to write down the end point of my lambda, which is 0.091 lambda here at the ring which is labeled wavelengths towards generator. The difference between gives me the length of the transmission line, which is 0.091 lambda minus 0.422 lambda. Since we cross the zero line here, the counting starts over again, and we have to add 0.5 lambda, otherwise we end up with a negative value. So putting this together, we get a total length of 0.169 lambda. Let's write down this value. So my length of my line output side is 0.169 lambda. That would be this line. Now let's do the same thing for the an open stub, which replaces a capacitor. This can be done using this Smith chart. Well, we want to create an open stub line that mimics a capacitor with a value 1.34J. Remember, that was the value of the capacitor. You can find this point here. We start with an open end, because we want an open-ended stub. And now we have to find the length of that line by looking at the starting point, 0.25 lambda, and the end point, 0.398 lambda. The difference between the two here is 0.148 lambda. Let's write down this number. Okay, we have to repeat exactly the same procedure for the source side, and we get again open stub line and an inserted line that converts my 50 ohm here to my gamma S here. Once you have done that, we end up with a matching network here on the load side, this one. This is the one we just designed, and we have to design a second matching network, basically the same idea, inserting a stub line open, it brings me here, inserting a line, brings me to this point gamma S here. That's my gamma S value. So the details about that you can try yourself at home. Now we end up with 4 different transmission lines. Load side, as we calculated, 0.169 lambda for this line and 0.148 lambda for the stub line. And when doing the same calculation here, you end up with 0.48 lambda for the inserted line and 0.192 lambda for the open stub line. This finalizes my theoretical design. And the next step now is to implement this design into Microwave Office and check if everything went right. Okay, let's convert this circuit now into Microwave Office circuit. You see the details of the amplifier. We have the transistor in the center, we have a line here and an open stub here, we have a line here and an open stub here. Both sides are terminated by 50 ohms, which are my 50 ohm ports of the amplifier. Let's go to Microwave Office. Well, remember, we imported the transistor already. We set the transistor to be at 2 volts VC and we set it to 3 volts IC. And now we have to add the lines here and the open stub lines here. Well, let's go to Elements, and under Elements we can go way up again. Let's close this library stuff. There are different models we can choose, and we go for the transmission lines here. Since we know the electrical length of the transmission line, we choose the transmission lines by phase, and we are in this tab. Here we can pick different kinds of transmission lines. TLIN is just an ordinary line, and the other one we need is TLOC, which means transmission line open circuit at the end. So just let's grab this one, add the line here, and add one here, and as an open stub, and place it here. Move down maybe the identifiers. The same thing on the other side. Grab a TLIN for the output to the collector, and a TLIN open circuit for the stub line here, and also maybe move the label here somewhere. So now let's connect this here and here, and now we need the ports. The ports you can find up here where it says just port, and pick one port to be on this side connected, and pick one port on the right side, and right click always rotates your element. I have to connect it here again. So now we have the schematic almost done. The parameters are wrong, but this mimics actually this circuit here. Now let's take a look here. At the input side we have a line which is 0.482 lambda long at 5 gigahertz. Remember, the length of the line, the electrical length of the line, depends on the frequency. We chose 50 ohm lines for all of them. That means this becomes 0.482 lambda at 5 gigahertz. I click here and say 0.458 lambda. Was it 458? 482, sorry. 482 lambda at 5 gigahertz. So 5,000 megahertz. You see here the electrical length must be given in degrees. 0.482 is the length given in lambdas. We can convert the electrical length from lambdas into degrees by just saying, well, 1 lambda is 360 degrees, so it's 0.482 times 360 degrees. So this is now the model of my transmission line, which has a length of 0.482 lambda length at 5 GHz and 50 ohms line. We do the same thing for the other 3 lines. I'm going to do this now without much comments. So next one is 0.92 lambda long. 0.921 times 360. 192, sorry. 192 at 5 GHz. This line here was 0.169 times 360 at 5 GHz. And this one here is 0.148 lambda, which is 0.360, also at 5 GHz. Just double checking, 0.148 and 0.169, which is here 0.148 and 0.169. Now that's it basically. Let's save our amplifier for later usage. Amplifier 1 maybe. And now we can simulate that amplifier. In order to simulate it, first we set our frequency range. Remember, we go to projects and then we go to project options, and here we can set our frequency range. We start at 1 GHz, we stop at 7 GHz, or let's start at 2 GHz, and steps of 0.01 GHz, and here we get a list of frequency points to be simulated and say, okay, now we have to display our results by adding a graph. We go here to graph, add new graph, we call it response, rectangular graph, and create it. Now we have a response here, and we have to add measurements to our response. Add measurements is here. We add S parameters from my amplifier, S11 in dB, amplifier, to port 1 from port 1 in dB, apply. We want the forward gain S21 in dB, apply. We want output match S22 in dB, apply, and we want the backward gain S12 in dB, apply. So that gives me 4 measured parameters, S11, S21, S22 and S12. The magnitude in dB. Say OK. The values are grayed out here because they are not simulated yet. That's why we have to simulate them by pressing this Analyze button up here. Now this simulates my amplifier, and here we can see the result. Maybe I move this down here somewhere. We see our typical result for maximum gain design. We get 2 peaks down at the design frequency, which is 5 GHz here. The blue line is my S11, which peaks down almost to 50 dB. The brown line is my S22, which also peaks down to about minus 50 dB, which means at the input and output at 5 GHz there are more or less no reflections. This is my gain of the amplifier, which is maximum here. It doesn't have to be maximum over frequency, but which has this value here. We can check this value by adding a marker there. Go add marker, right click, click it here, and now we see we are at 9.692 dB. Double checking this with my theory, remember, I calculated 9.7 dB as my gain of my amplifier. So that seems to work. Now we designed our very first amplifier that gives me 9.7 dB gain and is matched for input and output. That means that's my maximum design. These peaks down here, they don't have any meaning. They are just there accidentally. All the other frequency are not really nicely matched. In order to make the measurement to look a little bit nicer, I can change here in the properties my scaling of my x-axis from auto limits maybe to minus 50 to plus 20, let's say, and press apply. Now This gives me the response of the circuit in a nicer view. So everything is fine, and we've finished our design. Let's go back here. From theory to the first maximum gain amplifier. I can show you the results here again. So this would be the overall layout in Microwave Office, and that would be the overall response you should expect. Thank you for watching this little screencast. I would like to recommend you that you repeat all the steps with the BFP540 transistor for the given frequency and biasing points. Once you have done that, start your design using your own specifications and your own transistor. Thank you for watching. Bye bye.